Okay, so what we have seen from these graphs and what that last question was really trying to probe was the relationship between the steepness of the lines and the speed, or velocity, rather. So technically, what we saw is that the steeper the line, the faster the motion is, because if it's a steep line, it means it's covering a distance in a short period of time. And, in English, if we talk about the speed, let me share my whiteboard. If we talk about the speed, oops, let's go to black. We would say it's the distance over the time. In English, that's what speed is, distance over time. Velocity, we would say it's the displacement over the time. So because the displacement has a direction, the velocity also has a direction associated with it. Now, when we make a graph of x versus t, and maybe let me just draw a sample, something like that. Okay, so there's a sample graph. To find the displacement, we have to pick a time interval. So we might pick like maybe an initial time here and a final time there. And the displacement technically is the difference between this, which would be the x initial, and this, which would be the x final. So displacement, if I want to write it in English, or not in English, if I want to write it in math, I would say it is delta x, change in x. Hopefully you guys are familiar with the symbol delta. It's like a triangle, and it means change in. So change in x is a mathematical way that I would say displacement. And time, the time interval would be what we call a delta t. So we have a delta x being the change in the x coordinate from the initial moment to the final moment. And that's, we just picked two points in time on the graph and single those out. And we find the change in x and the change in the time during that interval. So we could say that the velocity is equal to the change in x over change in time. Now, technically, this is known as the, that should be like a little bar, which is called the average velocity. Okay, average velocity. That's the displacement over the time. And what average velocity tells me, it's kind of like if you left St. Louis at a certain time and arrived at Chicago at a certain time, and all we know is the displacement between St. Louis and Chicago and the time interval, and we assume you drove in a straight line somehow, instead of having to follow roads. The average velocity would give me, what the speed would be that would get you there if you didn't make stops. But of course, you might make stops, and the information provided doesn't tell you anything about stops. So in this particular case, if we started here and ended here, then the average velocity, let me use kind of brighter color, the average velocity would be the slope of the line connecting those 2 points. That would be delta x over delta t. And average velocity, while it's a useful concept, it's not really great, because what really happens between my initial time and final time is this object is sitting still for a while, and then it moves quickly, and then it sits still for another long while. And if we compute the average velocity, we get the slope of this green line, which is not a very steep slope. So the average velocity indicates a constant slow movement, when the reality was no movement and then fast movement and then no movement again. So we want to maybe be aware of this notion of average velocity, but we don't want to use it too much, because it doesn't actually capture the, what we mean when we're talking. However, for certain segments of this graph, the average velocity concept is really useful. So, for example, if we go, from here to here, so I'm making an orange segment. I hope that shows up. Maybe I'll make it a little lighter colored. There, the slope of that line, keep in mind that this delta x over t, that's the rise over the run, or exactly the slope. So average velocity is the slope. If my actual path kind of agrees with the line connecting the 2 points, then the slope of my orange line is exactly the same as the slope of the original red line, and the slope in this case would be 0. So we have a 0 velocity. And for any segment that is straight, the slope of the line connecting the initial and final point is exactly the same as the slope of the line. And so for straight line segments, we can perfectly say that the velocity during that segment is exactly the slope of that line. And that's a really important concept. That's what you guys were seeing in that last example. But when we get to a curving line, like the end of this, that kind of breaks down. Okay, when I have a curving line, in words, if I were to describe what is happening in this curving line, I would say, first of all, this object is moving at 0 velocity, so it's sitting still for a while. And then it starts moving back in the positive direction, but it's pretty gradual. The slope in this little area is pretty slow. But by the end of it, the slope is pretty big. So this must be an object that is speeding up. It doesn't have a constant speed. And if I wanted to find the average velocity in that time interval, maybe of that whole curve, I would get a slope of a line, and that slope is, well, I mean, it's okay as an average, but it doesn't capture the fact that this was maybe moving pretty slowly at the beginning, and at the end, it moves quickly. So we want a better concept than the average velocity concept. We want to define something called the instantaneous velocity. Any questions before I move on about the average velocity concept? Let me summarize it again real quickly, just to make sure we're all getting it. If I have a straight line segment on a graph, then the slope of that line exactly tells me the velocity during that. And there would be no difference between the average velocity and the velocity at any point on that line. But when the line starts changing, even if it just changes with like an angle, or it changes because of a curve, then the average velocity concept doesn't really work properly. Just to give you, analogy why it doesn't work. Just imagine pandemic is over, and so you decide you're going to drive to Florida and finally go to the beach, because maybe you wanted to do that for spring break, but maybe you prudently decided not to do it, or maybe you did it anyway and got lucky, but you're going to go again. And so you're driving, through Mississippi, and you go through this town of like 12 people. They have 11 people and a police officer, and the police officer's salary is paid by just catching people like you speeding through his or her town. And so you're driving through this town. Okay, let me revise that. They have 2 police officers. They have 10 people and then 2 additional residents who are police officers. And they have a speed trap. They have 1 officer at mile marker 172 and 1 at mile marker 173. And you're driving along. You're so excited to be out of the house and out of St. Louis, and you're going 90 miles an hour, and you pass the first mile marker, and after 40 seconds, you pass the second mile marker, and the police officer at the first marker has their radio and say, "Okay, here he comes," and they start a stopwatch. And the second one says, "Okay, they're coming, and now," they stop the stopwatch. 40 seconds. You went 1 mile in 40 seconds. That's 90 miles per hour, I think. So they give you a ticket, right? You get a ticket, 90 miles per hour. Now you go to Florida, you're bummed about the ticket, but you have a great time, and now you're back. So the first time your graph looked, it looked like this. All right, or maybe it looked like that because you're going really fast. I want to make it red. I'm going to try to make it red. Okay, now the next time you come back, you pass the first police officer, and then you slow way down, and then you go back up to 90, past the second police officer. And when they are, recording the time, it took you a really long time to get to, this point. And if they compute your velocity, your average velocity, it's the slope of this blue line. When in reality you did is you were driving 90, and then you slowed down to 10, and then you drove at 90 past the second police officer. And when they compute your average velocity using their method, they think that you were only going 45, even though their eyes tell them you were going faster. So that's a problem with the average velocity concept, and the police are well aware of this. Probably, 70 years ago, this is the method they might have used for a speed limit if there were speed limits then. But now they have radar or laser. It basically hits you with a beam. It hits you with another beam like a millisecond later, and it tells how far you traveled in that time. And there's just no time for you to speed up or slow down in that tiny time interval. And so their reading of your velocity gets much closer to your actual velocity during that time interval. So to do the average velocity concept, let me draw a graph. And suppose we have motion that looks something like that. We want to interpret this motion. If I want to find the average time or average velocity, I pick 2 points, maybe this point, and I connect them with a line, and I find the slope of that line. And that average velocity concept is terrible for capturing what's really happening, because in this case, what's happening is this object's moving in the positive direction for a while. It gets to some kind of maximum point, and then it starts to backs up for a while. It gets to some, lower point and stops, and then it turns around and starts going forward again. Okay, so there's all this stuff happening in between my 2 points, and the velocity misses it all. So what we do is we don't want our second time to be right there. We want to sort of slide that second time along our curve. Yeah, it's harder to do than I thought it would be. Okay, so that they're pretty close together. Then when I find the average velocity between those 2 times, it looks pretty close to what the actual curve looked like. And in fact, then what we would want to do is move them as close together as possible. So imagine I could put them right next to each other and draw a straight line through that curve. In fact, what I would like to do is get them as close together, so close together they're really touching. And then when I draw a line through those 2 points, what I'm really getting is the slope of a line that is what we would call tangent to the curve, which means it just touches it really in 1 point. So the idea is the slope of the tangent line. Again, what is a tangent line? It's a line that if we took those 2 points, slid them together until they're touching so that they really form 1 point. We want the slope of a line that just grazes the curve at that 1 point. We don't want something that crosses at that point. It cannot cross the line, or it shouldn't cross the line unless something really weird is happening with the line. It should just graze the point and not cross the line. And if we find the slope of that tangent line, that equals the instantaneous velocity. We would say that this object is going at this moment. That point defines the moment that it's going at the speed that is equal to the slope of that tangent line. Let me pause. I will see if you have questions, because this is kind of an abstract idea and you've been awfully quiet. Do you have any questions? Let me rephrase that. Ask me some questions. I know you have questions.
I have a question.
Okay.
Whenever you're picking your points and you're sliding them together, how do you choose at what point at the line you put the dots, or does it not really make a difference?
Yeah, the idea is really what we would do is we would pick the point where we want to know the velocity. So for example, maybe I want to know the velocity right here. So, we could pick a point here and a point there and sort of slide them both together until they meet at that point. Okay. So, going forward, we don't actually, so this is a concept. We're never going to actually slide 2 points together and try to do this. We just want to sort of have this idea in our mind. If I want to know the velocity at this point, then I just have to get my ruler and I move this line to that point. And then I have to kind of adjust it until, this is a little harder to do with a digital ruler, but maybe something like this, and then I'm going to try to adjust it until I feel like it's just grazing the line at that point. And once I have that, then I draw my straight line. And then I can now measure the slope of that straight line. We know how to find slope of a straight line from math class, but we don't know, unless we've had calculus, how to find the slope of a curving line. Well, this is how you do it. You define the slope at a point as the slope of a tangent line at that point. So, and again, we're not even going to be drawing tangent lines. I just want us to be able to have this concept. So by having this concept, what we can do is we can look at this red curve and we can visually see when it's fast and when it's slow, because at the beginning we can imagine that the tangent line is, kind of steep. Well, that was a bad line. But, at the beginning, the tangent line is steep. And if we just look at tangent lines at different points, we can see now a progression, what's happening to the speed. And in particular, we want to know, when is it fast, when is it slow, when is it stopped, when is the velocity positive, and when is it negative. And the tangent line gives us all of that information. If the tangent slope of the tangent line is a positive slope, remember positive slope in math is like up and to the right, then the object moves in the positive direction and it has a positive velocity. If the slope of the tangent line is negative, meaning it goes down and to the right, then the velocity is a negative number. The steeper the slope of the tangent is, the faster it's going. And really important, the special point is at the top or bottom of the curve where the slope of the tangent line will be 0. Those are the only points where this object is at rest, where it has stopped. And so we really want to be able to just look at a graph and visually see when is it moving in the positive direction, when is it moving in the negative direction, when is it stopped, when is it fast, and when is it slow. Okay, so that's a great question. Any other questions? Okay, so now we can define, because we can talk about how the slope is changing, we can define acceleration, which is our second, key concept. From today's lecture, the key concepts are velocity and acceleration. And we need displacement sort of to get there. So maybe 3 key concepts: displacement, velocity, acceleration. And just as we can say velocity, the average velocity is delta x over delta t. And we can say the instantaneous velocity. And after today, we're not going to really talk average very much. We're going to only be talking about instantaneous velocity, and so we'll just call it v. And when we say v, that will be already an instantaneous velocity. But the way we would mathematically describe this is we would say the limit as delta t approaches 0 of delta x over delta t. And before you let this mathematical definition, concern you, we don't want to think in terms of the mathematical definition unless you're just a really, a math person that likes math. What we want to think of, this is a mathematical way of saying, take those two points, slide them together until they're touching. That's what delta t approaches 0 is. That time interval shrinks to nothing, and find the slope of the tangent line. And so this is a mathematical way of saying, what we just showed with the picture, that the instantaneous velocity is the slope of the tangent line at a particular point. And so we can define acceleration as follows. It's the change in velocity over the change in time. Okay. So technically, this would be the average acceleration. We would write that as a with a bar over it equals delta v over delta t. And we're not really in this class going to have a lot of situations where the acceleration is changing. And so we'll get away with just calling this a. That is, the a will be constant in the problems that we are doing. And so because the acceleration is constant, when something's constant, you don't have to call it average, right? If you get a 90% on every single test and homework and everything you ever do, your grade is just 90%. You don't have to think, what's my average grade? Your grade is equal to your average. Okay, so let's see how we can see that acceleration in a graph. I'm going to go ahead and grab a piece of this graph to use. Ow. Stop, I don't want to tilt you. I don't know what this thing is sort of doing its own thing. Ah. Okay. So I have this graph, just a section of a graph, and I want to talk about the acceleration. So what's happening is it has a high positive velocity at first, and then its velocity becomes a smaller velocity, and then even smaller, and then it becomes zero, and then it becomes negative, and that's where it stops. So what's happening here? The velocity every second is decreasing. So maybe it started with 5 meters per second, and then it was 4, that should be 4 meters per second, and then 3 meters per second, 2 meters per second, 1 meter per second, then 0 meters per second, and -1 meters per second, -2 meters per second, and so on. This is sort of the progression if we drew more tangent lines. So to find the acceleration, we would do change in velocity, maybe 4 minus 5, or 3 minus 4, or 2 minus 3. We always take the final minus initial for a time interval. The point is we're taking 4, subtracting 5, so we get a negative number. Or 3, subtract 4, we get a negative number. Or even 0, subtract 1, we get a negative number. Or -1, subtract 0. We are always, over this whole curve, we're getting a negative number. And so we would say that the acceleration is less than 0 for this curve. It's always negative. Now, what would be nice, in English we use the word acceleration, but we have this other word, decelerate. We have accelerate and we have decelerate. And in physics, we don't have two different words. We just have acceleration. And an acceleration could be a speeding up or a slowing down. In English, accelerate means speed up, decelerate means slow down. And it would be really nice. Oh my gosh, do you know how much time in my life it would have saved me if this were true? If it were the case that positive acceleration means speed up and negative acceleration means slow down. That's what I wish were the case with the way English works. I wish accelerate meant positive acceleration and decelerate meant negative acceleration, because linguistically that makes perfect sense to me, but that's not actually how it works. If we look at the graph that I've just shown you, this is an object that's going fast and slowing down for a while. It stops momentarily, and then it starts to speed up in the negative direction. Okay, so this is what would be happening if you were driving along the road and you saw like a bar of gold on the side of the road. You'd like hit the brakes and then kick it in reverse and start speeding up backwards, because you'd pass it up, put it in reverse, and start backing up. The whole time you're doing that, you have a negative acceleration. Negative acceleration really just means that to get the new velocity, you subtract a number from the old velocity. So in the case of these numbers I made up, you're always subtracting 1. You subtract 1 to go from 5 to 4, and then you subtract another one and another one and another one. You get to 0, and you keep subtracting. And after -2, you're going to subtract 1 again and get -3. So that's what makes it a negative acceleration, because you always have to subtract a number to get the new velocity. Now, unfortunately, this is always a negative velocity. And I'm going to draw two graphs now to show you. But let's see. Oh, let's just extend this. So we just looked at one that looks like that. It curves downward, and we could also have one that curves upward. And there's different possibilities. But this has a negative acceleration, this one here. And this one has a positive acceleration. What that means is, to get the new velocity, we always add something. If we look at the picture, it starts off with the tangent line would be a steep negative line. So it would have a very large negative velocity. And to get the next velocity, maybe it's -8, the next one might be -7, and then -5, -3, 0. We always have to add a number to the previous slope to get the new slope. So that's what makes it positive. But there's a really easy way to know whether it's going to be negative acceleration or positive acceleration from looking at the graph. And again, I should stress that this is just always so far a graph of x versus. And this is called the double zero test. It's a really cool test. Some of you might have seen this before. But the trick is, you're going to love this test, I promise. You just draw 2 zeros above the curve. And if those 2 zeros don't make it clear that the first curve is negative and the second curve is positive, you may have to draw a big zero around them if it wasn't clear yet. This is the negative acceleration, and this is the positive acceleration. So you can tell if the acceleration is positive or negative just by looking to see, is the curve happy or sad? Okay? If it's not happy or sad, maybe we have a graph that just looks like that. We draw our 2 zeros and we say, I guess it looks a little sad to me, but it's neither happy nor sad. No acceleration. Or we could say A equals 0. If the line is straight, the velocity is not changing because the slope is not changing. And if the velocity doesn't change, there's no acceleration. Okay, any questions about the double zero test? Okay, in English though, if we look at this first sad curve, it's an object that's moving in the positive direction and it's slowing down because the slope is getting closer to 0. But then it starts speeding up backwards. See, slowing down means the slope approaches 0, and speeding up means it goes away from 0. This is slowing down for a while and then speeding up, and the whole time the acceleration is negative. The second curve, the happy curve, is also slowing down because the slope is approaching 0, and then it's speeding up. It's slowing down, moving in the negative direction, and then it speeds up in the positive direction. Any questions about that? Okay, I want to try another conceptual question. So we're going to do the same thing. You're going to look at this for a couple of minutes. You're going to vote. And then depending on what the votes look like, we will have breakout rooms and a little, you guys can have a discussion, and then we'll return to the main room. So take a look at this question, give you a few minutes, and then we'll vote. Okay. I think you can't vote on that. I think I need to like kill the poll and then make a new one. So if you have an answer, go ahead and vote. But if you're not ready yet, that's fine. You have a little more time to think. Haley?
Okay, so just to be clear, you said that if it's slowing down, it's approaching.
Hold on 1 second. You know what? I don't want to do any questions until we have finished the poll. So I want to get sort of your gut instinct, unless something was unclear about the question. Okay, if you haven't voted yet, go ahead and vote just your best guess. Doesn't have to be right, doesn't matter, just your best guess. Go ahead and pick it now. And then one more person, just pick something. Your best guess. Okay, maybe they're not here. Okay, so we see a spread of guesses. There's no clear majority this time, and this is normally what we're going to see on these polls. Okay, it is typically the case that you know, it's not clear at first, and that's what I'm looking for, because these exercises, they're not test how smart you are. They're let's see what you're thinking, and sort of, you know, you're going to have some pieces and other people are going to have other pieces, and then we, you know, through the dialogue, we'll all get a better understanding. So I'm going to stop the recording again. I'm going to put you in breakout rooms. This time I want a full throttle debate. Convince the people in your room that they're wrong and you're right. Be bold, be confident, be strong, and we'll have fun.